Math 1314, Chapter 6, Matrices and Determinants, Section 1, Matrix Solutions to Linear Systems, Video 3, Row Operations. In the previous video, we introduced a form called row echelon form and why it's beneficial when solving a system of linear equations. But the problem is most matrices aren't in row echelon form. And the question is, how do we take a matrix, and more specifically an augmented matrix that's not in row echelon form, and make it into row echelon form? And the answer is using something called row operations. Now, before we get into row operations, I want to convince you that you've been doing operations in math classes for as long as you can probably remember. Because in general, an operation is a process that takes one or more of an object and creates a new object. You already know some of these operations. We're about to remind you of what they are. Here's some operations that you already know. You know that operation because you can take two numbers and create a new number. So now, okay, yeah, I know a lot of our operations. I know this one. I can say something like 11 minus -5 and get 16. Think about it. Or I can say something like 3 times 11 and get 33. Or I could even use decimals and say something like 8.4 divided by 2.1, which would give you exactly 4. And there are also operations that only require a single number. For example, if I gave you this operation and put this number underneath it, then you would create a new object. You'd create a new number. There's a variety of operations that you've seen before. Maybe you remember absolute value. If I put a number like -5 inside an absolute value, that's an operation that turns it into a new number. So you've already seen operations before. So it won't surprise you that a row operation is an operation performed on one or more rows of a matrix that preserves the solution to the system of equations the matrix represents. Such matrices are called equivalent, meaning that they represent the same system with the same solution. There are 3 row operations that we're going to look at. Row operation number 1, you may interchange any 2 rows. This is what's called a row swap. Number 2, you may multiply a row by any non-zero constant, and this is what's often called scaling. You scale it up or down by multiplying it by a large number or a small number. By small, I mean a number less than 1. And the third one is you may add a multiple of one row to any other row, and this is called combining. Now, you don't have to remember the names of the moves, but there are notations for each one that you're going to run across in your homework. So let's take a look at them one at a time. Row swap. The notation to indicate a row swap looks like this. Now, the capital R stand for rows, and the J and K represent numbers, which row you're looking at, with the double-headed arrow in between, meaning that you're swapping out the 2 rows. For example, we're going to perform the row swap R1 with R3 on the following matrix. I'm not going to read the numbers to you. You can see them right there. But when you perform a row swap or any row operation, on the right of the matrix, you write the operation that you're doing. So R1, double-headed arrow, R3. Now you can write the numbers subscripted. I just can't type them subscripted. And all this means is we're going to take these 2 rows, the first row and the third row, and literally switch them. So how will that look? Well, we'll draw another arrow pointing to the right, saying that we are about to turn the first matrix into this matrix. Now, I'm reluctant to put an equal sign because they are not equal. The only way 2 matrices are equal is if all their numbers match exactly. Let's just say that this arrow is the symbol for the word is equivalent to, or the phrase is equivalent to, meaning that although we're changing the look of the matrix, it's not changing the system, and more specifically, the solution to the system. So let's swap the 2 rows, and this is the easiest of row operations. The third row will become the first row. So 1, -3, 1, -1, 3, 7 on the top. The first row becomes the third row. So on the third row, 3, 7, 4, and 1. And we didn't affect the second row, so it stays the same. 0, 2, 6, 10. And that's all there is to a row swap. You literally swap 2 rows. In this case, the third row became the first row, and the first row became the third row. Although drawing those extra arrows is unnecessary, this notation here totally captures the move. So swapping 2 rows, not too bad. And if you're wondering why would we do this, because eventually we're shooting for row echelon form. And the first non-zero entry in the first row should be 1. And by pulling off a row swap, we managed to actually get the number 1 right there as our first pivot. Now, that's not why you always do row swaps, but that's one reason to do it, to get a 1 in the right place. All right, so let's take a look at the next row operation, scaling rows. And again, scaling just means to multiply up or down. Like when you scale on a map and you say 1 inch equals 100 miles or something like that, you're scaling it down by a factor of, well, however many inches are in 100 miles, which would be a lot. All right, but anyway, the notation to indicate scaling, and this looks more complicated than it is NRJ, where J is the row and N is the scaling factor. In other words, the number you multiply by. And it usually looks something like this. Form 1/2 R2 on the following matrix. And all that means is we're going to take 1/2 times the second row. Now the scaling factor, in this case, the 1/2, it can be a fraction, it can be a whole number, it can be positive, it can be negative, it can be anything except 0, because that would kill the whole row. So we're going to perform this row operation. And again, the way you write it is to the right of the matrix, you just write what you're going to do to it. We're going to do 1/2 of the second row and get an equivalent matrix. All right, well, if we take half of the second row, let's highlight the second row for emphasis. We take half of the second row, half of 0 is 0, half of 2 is 1, half of 6 is 3, half of 10 is 5. Now, when you do a scale, when you scale a row, you don't change the other rows. So the first row stays the same, 1, -1, 3, 7. And the bottom row stays the same, 3, 7, 4, 1. So it's not a difficult row operation to do. The hardest part about row operations is deciding when to do them. And we'll get more into details of that, of making those decisions later. But scaling a row is just multiplying it by a number. Now, the third row operation, combining rows, this takes a little bit more focus because you're doing 2 things. The notation for combining rows is NRJ plus RK. And again, don't let the letters throw you off. This means you multiply the jth row, whichever row you're looking at, by some number n and add the results to the kth row. Let me put that in English. You're going to pick a row, multiply by any number you want, and add the results into a new row. For example, we're going to perform the row operation -3R1 plus R3 on the following matrix. Now, what this means is we're going to take this first row and multiply it by -3. Now, it's important to point out that when you do this move, you're not actually changing the first row. The first row is going to stay the same. You're simply temporarily multiplying it by -3 so that we can add it into the third row. So we're going to do -3 times the first row and add the results into the third row. Let's start by documenting our move. -3 R1 plus R3. Now you may want to write some of this out, but I'm going to do it bit by bit. All right, so let's start with the first column. We're going to take the number in the first row and multiply it by -3 and add it to this number down here. So let's talk it out. What is -3 times 1 and then added to that 3 down there? Well, -3 times 1 is -3 plus 3 is going to give us a 0. Now, the results always go into the row into which you are adding. And since we are adding into the third row is where we're going to document our results. Let's do the same thing for the next column. Again, for this particular row operation, we are taking the number in the first row, multiplying it by -3 and adding it into the third row. So for the second column, we would take -3 times -1 and add it into the third row, which is a 7 waiting for us here. 1 second, folks. Sorry about that. I had to reply to a text. Where were we? We were adding -3 times the first row into the third row, and we were focusing on the second column. So in the second column, looking on the top row, we're multiplying -1 times -3, adding it to the 7 below it. -1 times -3 is +3. +3 plus 7 is 10. And we have to do it for every column. In the third column, we're going to multiply, and I'm running out of places to write these things here, so I'll just scoot over a little bit more. In the next column, we're going to multiply -3 times 3 and add it to what you see in the third column, which is the 4. -3 times 3 is -9. -9 plus 4 is -5. And maybe I should have kept these numbers color consistent. Give me 1 second and I'll fix all that. Okay, I've changed the colors into the results to match the colors over here. So the yellow 0 came from doing the yellow math, the blue 10 came from doing the blue math, the orange -5 came from doing the orange math, but we have one more column to do all this to. That would be the last column, the augmented column, if you will. We are going to take -3 times what's in the first row, which is 2, and add it to what's in the third row, 1. -3 times 2 is -6. -6 plus 1 is -5. Only that column changes. The first column stays the same. 1, -1, 3, 2. The second column wasn't even involved. Excuse me, the first row stays the same. The second row wasn't even involved, so it stays the same. It's only the row that you are adding into that changes. Now, this is the trickiest one to not only understand, but to execute, because you're constantly saying, what am I multiplying by what, and who am I adding it to? And then writing the results down there. All right, so that's how you combine rows. And the notation, again, is just to multiply a certain row by a certain number and add it into another row. All right, so those are all the row operations. Now, if you paid close attention, you noticed we performed a sequence of row operations on one matrix. I've got them documented here, but let's go back over here. And for some reason, I don't have what I thought I would have over there. Let me see if I can figure out where I went astray. I did. Okay, look at the top row on both of those. They end in 7, right? Yep, they do. For some reason, when I started this one, the top row ended in 2. Well, this wasn't supposed to happen. I thought I had this all set up perfectly. So I'm going to reconstruct what was supposed to happen here. And it'll give you an opportunity to follow along one more time as we execute this last column when we did this row operation. So we need to get rid of this, and we'll need to get rid of that. So let's perform the last one more time, shall we? All right, that was supposed to be 7 on top. If we're still doing the same row operation, so -3 times whatever's in the first row, -3 times 7, add it into whatever's in the third row, which is 1, and that equals -20. That was supposed to be there. But as I was trying to say, if you noticed, and maybe you didn't because of this error I just corrected, we actually performed a sequence of row operations on the original first matrix. If you'll notice, the first matrix is there, and then we changed it into this. Let's highlight in purple. We changed it to that matrix, which happens to be this matrix. And then we changed it to, running out of options here for colors, and we changed it into this matrix, which was supposed to be this matrix. And then we ended up with that one at the end. So this kind of summarizes that sequence of row operations that we performed. We started with this matrix, did this row operation to it to create that matrix, did that row operation to it to create this matrix, and then did this row operation to it to create that matrix. And if you're wondering why bother, well, take a look at the last matrix. Is it an echelon form? It almost is. At least it has the makings of it, because the last matrix, the first non-zero entry in the first row is 1. The second non-zero entry in the second row is 1, but the first non-zero entry in the third row isn't 1. We do have some zeros below the first pivot, but we don't have 0 below the second pivot, and we don't have the first non-zero entry in the third row equal to 1. But this matrix is almost in row echelon form. And we can actually achieve row echelon form with 2 more row operations. I'm only going to execute the first one, and then I'll describe what the second one was. But if you keep in mind the goal of, sorry, there's a dog at my feet, the goal of row echelon form is to get a leading one in each row and zeros underneath each of those ones. Well, we don't have a zero underneath the second one. In other words, we don't have a zero right here, but we can perform a row operation to get that zero. What's that row operation? Well, we can do -10 times the second row and add it into the third row. Because think about it. If we multiplied the second row by -10, then this one would become a -10. And when we add it to the 10 below it, it would make that 10 become a 0. So let's see how quickly we can pull off this move, shall we? Top row staying the same. Second row staying the same. I know it says we're multiplying the second row by -10, but that's just a temporary change right before adding it into the third row. So let's see what happens when we multiply -10 times the second row, add it to the third row. Let's start with, let's pick a color. Let's pick this color. Let's start with the 0. And if we multiply it times -10 and add it to this, well, that's easy. -10 times 0 is 0, plus 0 is still 0. Okay. What happens if we multiply -10 times this number and add it to the number below it? Well, -10 times 1 is -10, plus 10 gives us 0. What happens if we do the same thing here? Well, -10 times 3 is -30. -30 plus -5 is -35. And if we do the same thing over here, -10 times 5 is -50. -50 plus -20 is -70. And if you'll notice, that almost gets us row echelon form. We have the ones here. We have the zeros below. Put that back over there. The only thing that we're lacking is a 1 there. I wonder how we could get a 1 there. Well, how about we multiply the third row by something that will turn -35 into 1? Now, what can you possibly multiply by -35 to turn it into 1? And the answer is -1/35. If we pulled off this last row operation, then this matrix would now be in row echelon form, which means the system it represents would be pretty easy to solve. Now, if you're wondering or worried about how do I make these decisions that will get me from non-row echelon form into row echelon form, it's actually very straightforward. You just got to know where to focus and what row operations to do. So in the next video, we're going to summarize how to take a matrix and perform a sequence of row operations to convert it into row echelon form.